Okay, so today we're going to be talking about the digital simulation of lattice gauge theories on quantum computers, and we're going to be looking at some work I did with Natalie Clow and Martin Savage. But before we dive into our work, we're going to just give a quick overview of what lattice gauge theory is and why you should care about it. So in physics, one of the most important features of any theory are the symmetries of a theory. In particular, local symmetries are incredibly important because having a local symmetry or a gauge symmetry requires an introduction of gauge fields. And so these gauge theories are ubiquitous throughout physics and particle physics. A U1 gauge theory describes electromagnetism. SU2 gauge symmetry describes the weak interaction. SU3 describes QCD. You can even view gravity as a form of gauge theory, where the gauge group is given by the Lorentz group. And then these also show up in quantum information. For example, surface codes can be viewed as studying the ground state of Z2 lattice gauge theory. And these theories also show up in all over condensed matter, describing many different kinds of topological order. And so to do calculations in gauge theories numerically, we need to discretize space. And so we do that by placing our matter fields on the points of a lattice, where under a gauge transformation or a gauge symmetry, they transform in this way, where G is some member of the gauge group. And to get terms in our Hamiltonian that are invariant under this transformation requires an introduction of link variables, which are the lattice analog of gauge fields. So under a gauge transformation, they transform in the following way, where this end is multiplied by the gauge transformation at this vertex, and this end is multiplied by the gauge transformation at the other vertex. And so you can construct gauge invariant operators this way by taking products of matrix fields, where products of the matter fields, where this creates a particle at one site, this transports along the link, and this one creates a particle at the other site, this one annihilates. And you can tell from these two equations that this is invariant under this symmetry. And then you can also construct other gauge invariant operators by taking the product of these link variables going around in a closed loop. So for example, we can look at the Plycat operator defined here, which is the product of the link variables going around this square here. And the Plycat operator is the lattice version of the magnetic field. So like I said, we're going to be talking about the quantum simulation of lattice QCD, which is the theory that describes the fundamental interactions of quarks and gluons, which make up nuclear physics. Some aspects of lattice QCD can be simulated on classical computers using Monte Carlo simulations, and these Monte Carlo simulations have been incredibly successful in computing many aspects, such as hadron masses, such as the mass of the proton and neutron. It's very good at simulating high temperature and low density systems. You can use it to extract some low energy scattering amplitudes. And it's also used in the theoretical prediction of the value for mu on G-2. And so although these simulations have been incredibly successful, they require an incredibly large amount of computing power. And there are some variables of interest who computation encounters a assignment problem on classical computers. This is where quantum computers come in. So our hope is that we can use quantum computers to compute observables in lattice QCD that are not accessible on a classical computer due to assignment problems. So for example, simulating real-time dynamics. So one situation that would be of a great deal of interest would be simulating the short time collision of two protons, because this is a process that is pretty much described by QCD, but is not something that we can really do from full first principles. And then also other things that may be of interest on quantum computers would be simulating finite density systems and chiral gauge theories, both of which encounter assignment problems on classical simulations. So to do a simulation of a quantum simulation, we need to map our theory onto a quantum computer. So today we're just going to be talking about the gauge the link variables. So we can put this on a computer by assigning assigning qubits to each link on our lattice. And so we have a couple of choices for what these qubits can represent. So there's a very large number of different strategies people have looked at, but generally either you're going to look at discretizing your gauge group in some way, or you're going to work in the representation basis or the electric field basis. So in this basis, each link you specify the representation of the group on that link along with index on the left side of the link and index on the right side of the link that specifies which element of the representation is present. And so this electric field basis is subject to a constraint called Gauss's law. You might remember from freshman physics that Gauss's law tells us that the amount of electric flux going in is equal to the amount of electric flux going out. And this carries all the way over to lattice gauge theories as well, where at this vertex, all of the representations here must add up to a singlet state. And so once we have an assignment of our theory to a quantum computer, we need to construct Plycat operators, which, as I mentioned before, are the lattice version of the magnetic field. So these will be defined on a product of 4 links, and we just need to know what it looks like on one region of the lattice because of translational invariance. So we know what the Plycat operator looks like here. We know what all of these other ones will look like too. So the quantum simulation of lattice QCD has been investigated before in the work of Burns and Yamamoto in 2006. So they looked at using the Qdits Hamiltonian given here, where this is just a sum over all of the magnitudes of the electric field on all of the links, and this is a sum over all of the plaquettes on the lattice. And so at each link you have in the electric field basis the representations of SU3, where P and Q specify the representation, and these specify which element of the representation you're in on the left side, and this specifies the elements on the right side. And so because of the constraints of Gauss's law that requires the introduction of Clebsch scoring coefficients into the wave function, which enforce the constraint that all the representations at a given site add up to a singlet. However, it's not necessary to track all these degrees of freedom because we can just solve this constraint exactly. And so if we partially solve at each site, we know that since all the representations have to add up to a singlet, we don't actually need to track these 3 degrees of freedom because they are entirely fixed by the Gauss's law constraint. So for each link, we only need to track what P and Q are, or in other words, we just need to specify the representation. And that's all we have to do to map our basis to a quantum computer. This has previously been investigated for SU2 by these people. So let's talk about what this looks like in a bit more detail. So here we have a single plaquette connected to 4 links. And so we can describe the full wave function of this system with this following basis, where each of these is the representation on one of these links. So here we have a sum over all of the elements of the representations on each of the links, along with Clebsch scoring coefficients that enforce the constraint that then at each of these vertex, these 3 representations add up to a singlet. And so in this basis, the link operator takes the following form, where it changes the representation on the link and then also adds in some more Clebsch scoring coefficients. And so you can compute with this expression matrix elements of the Plycat operator, which take this rather large form of a sum over products of 16 Clebsch scoring coefficients. And so we can perform the sum and extract all of the matrix elements of the Plycat operator. I should also mention that in this basis, the electric field energy is diagonal, and so it's much more trivial to compute, so we won't worry about it during the rest of this talk. So like I said, this has previously been investigated for SU2 gauge theories. So here it was in the work by Close, Savage, and Stryker, it was shown that the matrix elements of the Plycat operator are just given by the product of 6J factors, where you get one for each vertex. And then we showed that for SU3, the same sort of factorization happens, where you just get a product of 4 9R symbols. And this sort of where the 9R symbols are defined here, and this sort of factorization to the product of 4 9R symbols generalizes to SUN, where if you just replace these SU3 Clebsch-Gordan coefficients with SUN Clebsch-Gordan coefficients. So now that I've talked about how we're constructing our basis, let's talk about what the plaquette operator looks like. So if we look at this 1D chain of plaquettes where we have our qubits assigned to each of these links, the plaquette operator will, when we apply it to, say, this plaquette operator, this will change the representations on these 4 links. And the amplitude, size of the amplitude change will be controlled by these 4 control links. And so this might seem a little strange because I mentioned a few slides ago that the Blackout operator is defined as the product of link variables on these 4 links. And so you would think that it should only depend on only act on these qubits. But because we solved a constraint in each of these vertices, that forces us to pay a price in locality. So that solving that constraint introduces a little bit of non-locality into our Hamiltonian by introducing these controls. And you can see what happens in SU2 as well, where in each of these vertices, there's now 2 links connected outside of the plaquette. And we can view those as being combined into a sort of virtual link that acts as a control on the plaquette qubits. And that generalizes to D dimensions, where in general we'll have 4D control registers that we can always compile down into 4 virtual links. Okay, so now let's look at a more explicit example of what happens when we apply the plaquette operator. So here, let's suppose we have a 3 representation on this link, a 3 representation on this link, and an 8 here. And we apply the plaquette operator, or if we represent this in terms of P and Q, we'd have a 1 0 here, a 1 0 here, and a 1 1 here. So when we do this, the plaquette operator can change this link to either a 3 bar or a 6, and it can change this link to a 15, a 6 bar, or a 3. So we can just explore all of our options. So if we get a 6 bar here, that can be combined in a gauge invariant way with the other representations on the links at this site. So that's going to show up when we apply the plaquette operator. Same thing with the 3. However, if we get a 15 here, there's no way to combine these to form a gauge invariant state. So that term, the state won't show up in our plaquette operator when we apply it to this natural state. But the state with the 15 at this vertex is still in the Hilbert space because we're representing each of the links with a set of qubits separately. So there's part of our Hilbert space that is not physical. So let's talk a bit more about what this assignment looks like. So at each link, we're assigning a set of qubits or Qdits that store the value of the representation on the link. So here we have a diagram of all the different low-lying representations for SU3, where this is the singlet down here. Then you have your 3 representation, your 3 bar, your 8, your 6, and your 6 bar. And these arrows show the representations that you can get when you apply the plaquette operator. So if I applied plaquette operator here, and I was in a 3 state, I can end up with a 3 bar or a 6. We can also represent this in terms of P and Q for the representations. And this representation is a little bit nicer to look at because the effects of applying the plaquette operator can either increase P by 1 or decrease p by I1 and increase q by 1, or just decrease q by 1. And so when we assign our qubits to each link, we can think of one set of qubits as forming a binary representation of p, and a different set of qubits forming a binary representation of q, which makes the effects of this a little bit easier to track. So now that we've talked about this local basis, we're assigning qubits to each link. We can also, this local basis still is subject to the Gauss's law constraint, where all of these links have to add up to a singlet, but there are some spaces in our Hilbert space that don't satisfy this constraint when we're assigning our qubits locally. We can avoid this by just by completely solving these constraints everywhere on the lattice. And so this is what we refer to as the global basis. So this requires a lot of classical preprocessing, which is not known to be scalable as far as we know. But when you work in this basis, you can project into local and global symmetry sectors. And so this lets us use all of the Hilbert space on our quantum devices, and the errors are not capable of violating symmetry because we've explicitly projected down into symmetry sector. So this global basis has a non-local distribution of information on the lattice. So while this global basis is not scalable, it can be mapped onto existing devices for small systems. So we're just going to take a quick stop here and look at what current devices are capable of simulating. So we can start by looking at simplest system with only gauge degrees of freedom. So a single plaquette where we have 4 links forming a square. So because of the Gauss's law constraints, we know that on each of these links, they have to have the same representation, because as Gauss's law tells us, the amount of flux coming into this vertex here is equal to the amount of flux coming out here, which forces all the representations to be the same. So you can look at this for SU2, where the Hamiltonian is given here. And for SU2, you can think of the Plycat operator as being a sort of finite difference operator, where, and if you look at it in this way, this Hamiltonian just becomes a discretized version of the harmonic oscillator. So we know that for the vacuum state, the wave function is going to fall off like a Gaussian. So as we increase the size of the representation, observables converge to their infinite truncation limit at a Gaussian rate. And this carries over to SU3, although this is not quite as easy to see. So here we have all the representations of SU3 mapped out at different points. And here is a heat map of the vacuum wave function. And so this takes the same sort of Gaussian shape as SU2. And here, if we look at the mass gap, or the energy gap between the lowest energy state and the first excited state, we see that as we increase the truncation, the rate at which it converges down to the infinite truncation value is Gaussian, which we can see from this log plot. So now that we've talked about what the wave function for the ground state looks like for this single plaquette, we can also talk about looking at performing time evolution. So one thing you might be tempted to do is expand the plaquette operator out in terms of Pauli matrices acting on all of the qubits we're using to represent the system. This is not a great decomposition to use for triatorization, because you end up with an exponential number of terms in the sum, or a number of terms exponential in the number of qubits you're using. A more efficient way of going about performing a triatorization is to expand in terms of raising and lowering operators acting on all of the qubits in your system. When you do that decomposition, you end up with n squared plus 2n terms in this decomposition, where n is the number of qubits you're using. And so the unitaries that are generated by terms of these forms are just 2-level unitaries whose circuit representation you can find in Nielsen and Schwank. So you can also look at working in the if you're interested in the dynamics of the trivial vacuum, so the state where there's no electric field to start off with, you can look at using the color parity symmetry, which takes advantage of the fact that the only states you need to consider are those connected to the vacuum by the trivial vacuum by this Plycat operator, which means you only have to consider states of this form, where you just have the sum over state and its conjugate, sum over representation and its conjugate representation. So, for example, the states that would lie in the trivial vacuum sector would be the trivial vacuum state itself, 3 plus 3 bar, 8, 6 plus 6 bar, and so on for higher representations of SU3. And so we can look at also using the symmetry on larger systems, but much like working on a global basis, in general, it does not seem to be scalable. So now I've talked a bit about how to do this triarization exactly. Abstractly, we can look at actually putting it on existing hardware. So we looked at simulating single plaquette on IBM's Athens chip. So IBM's Athens chip has 5 qubits with linear connectivity. The first non-trivial truncation that you can look at keeps the 0, 0 state, the 0, 1 state, 1, 0, and 1, 1. So we're truncating P and Q at 1, or equivalently, we're keeping the singlet representation, the 3 bar, and the 8. And the connectivity caused by the Plycat operator between these basis elements is shown by the lines here. So because this is this system has 4 basis states, we can map it down onto 2 qubits. So in this plot here, we start off in the trivial vacuum, so in this state right here, and then we perform the tritorized time evolution on the IBM Athens chip for 1, 2, 3, and 4 trotter steps. So in this calculation, and on IBM's chips, since the chip's noisy, we had to use different methods to mitigate the noise. So one of the noisiest parts of the circuits comes from the imperfect implementation of C0 gates, which can be mitigated by putting in more C0 gates and then extrapolating down to the 0 noise case. Then we also had to deal with the measurement errors in the measurement process. So one approach to doing that is to use the measurement calibration matrix inverse method that's known to Qdits. Another approach that was available to us because we weren't using all the qubits was to use majority choice voting. So at the end of this calculation, we performed C0 gates going down in this direction and used majority choice voting to mitigate the measurement errors. And we actually found that this majority choice voting correction performed in a comparable way to the measurement matrix inverse, which was rather surprising and encouraging. So by comparing the different results from using all these different methods to mitigate errors, we were able to get an estimate of the systematic uncertainties in this calculation. So the error bars on this plot are not just representations of the statistical error, they represent a full counting of all the systematic errors in the calculation. So now that we've looked at running with this truncation, we can look at raising the truncation and global basis. So the next representation that we would include would be the 6 representation, which would add these 2 basis states. So because this is now a 6-dimensional system, we would need 3 qubits to store the state of the system, but this presents us with a bit of a problem because of the form of the Hamiltonian. So here is the connectivity we have on the Athens chip. And this presents a problem because in our Hamiltonian, we have direct interactions between this qubit and this qubit, but they aren't connected directly. So we need to do some swap operations to interact with them, which gives us a bit of a significant amount of overhead. So if we had a chip with all-to-all connectivity as shown here, we only need 20 CNOTs to do a trotter step, but because of this linear connectivity, a single trotter step would require 38 CNOTs, which pushed it beyond the calculation, beyond the realms of what the device could do. But not all is lost because we can use the color parity basis I discussed on the previous slide. So in the coparity basis, we're essentially using the fact that this diagram of connectivities is symmetric about the horizontal axis. So we only need to store the states 1, 3 plus 3 bar, 8, and 6 plus 6 bar. And once again, this is a 4-dimensional system, which we can map down onto 2 qubits. And so the cost of doing a Trotter step is now down to a much more reasonable number of C-naughts. I see there's a question in the chat asking what majority choice voting consists of. For the majority choice voting, we started with, say, for example, this qubit is in the state 1, then we applied a C-naught to these 2 qubits. If there is no noise in the process, we measure these qubits to be in state 1, 1, 1. But if there was noise that flipped one of these qubits in the measuring process, say this one got flipped, we'd have a 1, 0, 1. But we know that the result should be a 1 because this qubit was in the 1 state and this qubit was measured to be in the 1 state. So we're in a sense, we're having the qubits vote on what the value of this qubit should be. So on this plot here, you might notice that the uncertainty at the peaks of the electric energy are a bit wider than the uncertainties at the other parts of the graph. So this led us to propose using the size of these peaks as benchmarks for how our calculation is performing. As we develop quantum algorithms for performing simulations of theories, it's going to be helpful to have benchmarks for different theories that give us an idea of how good of a job we're doing at simulating the theory. So for last gauge theories, we're proposing looking at the time evolution of the electric energy as a benchmark. And so in this plot here, we have the size of the first peak in the electric energy. So each of these windows shows a different truncation. And so for this truncating at 3, there's very little noise because you can do this all with single qubit gates. And then truncating at 8, we can see what happens as we add more Trotter steps. As we add more Trotter steps, this calculation becomes more accurate, but because of the increased circuit depth, the uncertainty in the calculation becomes wider because of the increased noise. And as we go up to 6, we looked at using first and second order Trotter steps. And so here we can see that the first order Trotter steps get nowhere close to computing the actual value of the first peak shown by this dotted line. But the second order Trotter steps work almost immediately. And so this is pretty encouraging because we have a method that theoretically should improve the result, but we would pay a cost of noise through the increased circuit depth. But we find that increased circuit depth is not a problem in this case, and we just get an improvement. So that is very encouraging to see. All right, now that I've talked about what we can do on local hardware, on existing hardware, I'm going to take a quick look at what we expect future calculations to look like using a local basis, where once again, we're assigning each link a set of qubits to represent the state. So the most non-trivial part in performing the time evolution is going to have to deal with the Plycat operator, which once again we've shown here, where find the Plycat operator changes the values on these 4 sets of qubits, and the value of the change is controlled by these 4 links connected to it. Or in quantum circuit form, we can view the 4 control links as just we can view this entire process in the quantum circuit language shown here, where these are the control links and these are the 4 links in the qubits. So one strategy that we looked at using to do this, we call it a gauge variant completion, where for the physical states that satisfy Gauss's law, we want to make sure we get the mapping between those correct. And we don't want any mapping between the physical and unphysical states. Then for the unphysical states, we don't care what happens to them as long as they map to unphysical states. So this gives us a good deal of freedom in how we're constructing our tritorized Plycat operator. So for example, if we knew that the only physical states had a 1 on this qubit, we wouldn't actually need this control because we don't care what happens when there's a 0 here, because our wave function should have no states with a 0 on this qubit. So this was done in previous work for SU2 by doing a close examination of the form of the Plaquette operator. For SU3, we would like to do this in a much more systematic way. And so we can do this by factorizing, by breaking the tritorized Plaquette operator into different control sectors. So just apply a different set of operators for each control sector. And so by performing this decomposition, all of these different terms commute with each other because each of these controls is just really a projector onto a different subspace. So we get no tritorization errors between these control sectors. So for example, we could look at forming a simulation where we truncate our representations at 1, 3, and 3 bar, or in other words, we're putting a Qtrit on each link. So when you do this, we end up with 27 different independent control sectors, which we've enumerated here. So when you perform the tritorization, you would first perform one in the sector where all control links are in the 1 state, then one where they're all in the 3 state, one where they're all in the 3 bar state, and so on until you've done all 27 sectors. And so these controlled rotations that you're performing can be represented using Givens rotations, where for a general Qdit, Givens rotation just performs a rotation between 2 basis elements of the Qdit. So you can write this out here in terms of sort of generalized Pauli operator, which is Hermitian, but not unitary for a general Qdit. And I should also mention that these Givens rotations can be pretty straightforwardly mapped down to 2-level unitaries that we discussed previously if you don't have access to Qdits and you're actually just compiling things down onto qubits. So for the Plycat operator in the 3 bar 3 control sector, you can write this part of the tritorization in terms of these 4 generators of Givens rotations acting on each of the Qdits in the link. And then these amplitudes are given by the plaquette matrix elements. And so you would have some unitary that looks like this in each different control sector when you perform the tritorized time evolution. And you can represent this all using these lines as Qtrits, where this takes a rather natural form in terms of how you would decompose the circuit. So for these simulations, we're going to think about composing things down into Qdits because this is a more close representation of what we're doing than just compiling down to qubits. So now one of the big benefits of compiling our tritorization in this format is that we will preserve the symmetries of our Hamiltonian, including gauge invariance and color parity. So with this tritorization, we're only mapping physical states to physical states, which is something that we would really prefer to do because that's a symmetry of our Hamiltonian. So in each of these unitary operators is associated with a physical Plycat transition element that we discussed on the previous slides. And so these coefficients can determine in a classical calculation beforehand. So here we have just are showing an example of the time evolution of a 2 Plycat system computed on a classical computer. So now let's talk about how this method scales. Since naively we'd expect there to be lambda to the 6 states at each vertex if there was no constraint on it, because we're trunking P and Q if we were trunking P and Q at lambda for each link. But that could be changed by applying Gauss's law as constraint. But what we found is that if you look at all the allowed states for a 3-point vertex where you have 3 links coming in, Gauss's law does not change the asymptotic scaling of the number of allowed states at a given vertex. Same thing if you consider 4-point vertices. And so when you look at the scaling of the number of rotations that you'd have to do for the plaquette operator as a function of truncation, you find that the naive lambda to the 16th scaling is actually what you end up with even in the presence of Gauss's law. So here we show the number of rotations you need as a function of the number of representations you're using, and it scales as lambda to the 16th as theoretically expected. However, this isn't as bad as it naively seems, because states with very large representations are going to be suppressed in the wave function. So to summarize this talk, we looked at simulating lattice gauge theory by mapping qubits to each link in the lattice. So the requirements, number of qubits required to do this scales linearly with the size of the lattice and logarithmically with the field cutoff. So for a rather modest calculation where we have a three-dimensional lattice where each side has a length of 10, and we're truncating, looking at the first non-trivial truncation for SU3, we would need 2,000 logical qubits to perform to store the state on a quantum computer, and to form a time evolution, we would need approximately 1,000 Givens rotations per plaquette. So this is large, but not necessarily impossible. Then we also looked at implementing the global basis on existing hardware and discussed how we could use this as a benchmark of existing hardware's performance. Then we also looked at a scalable way of doing a gauge invariant time evolution that we organize in terms of a local link Qdit structure. So, thank you for your time.